the next speaker is Tobias Kippenberg. He is the director of the Laboratory of Photonics and Quantum Measurement. He is the recipient of a number of prizes, award for his research in optomechanics. But today, he will give a speech about on the team which is on focus today, that is integrated photonics. And this might give a way to see how to save power on computers, on future computers. You have the floor, Tobias.
Okay, thank you for inviting me here. So I should clarify that even though I asked to talk about energy, I want today to talk really about a topic that I've been very passionate about for about 20 years. And that is how to control macroscopic mechanical oscillators that you can look under a microscope in the quantum regime and thereby prepare non-classical states of mechanical motion. And this is primarily an endeavor on precision measurements, understanding how to extend quantum control from atoms, ions, and molecules to engineered mechanical systems. And so that's actually what I'd like to talk about next 40 minutes, and also provides me some opportunity to tell about some early developments of the field and also some recent work actually that we have been involved in. Okay, so first of all, I'd like to mention that, of course, mechanical oscillators are objects that encompass us in our daily life. And so each of you actually have probably a 5G cell phone, and actually inside these actually are piezo-mechanical systems, so-called F-bar filters that convert actually microwave oscillations into mechanical piezoelectric vibrations that are used for filtering. At the same time, mechanical systems also use the motion sensors. So for instance, a car to measure acceleration, to measure kind of force, or also displacement. They're also used in timing, obviously, say quartz watches, and use here a high-Q crystalline oscillator that provides actually a signal of timekeeping. At the same time, mechanical systems have also been part of some of humans' most sensitive measurements. And I think the most remarkable example, at least to me, is actually that of the gravitational wave interferometry, LIGO and Virgo, and also new detectors that are being built, such as the Einstein Observatory, that are able to detect the minute gravitational energy that gravity waves deposit in test masses. And so scientists over a quantum measurement pursuit that extends now many decades are able to resolve the fluctuations that are caused by gravitational waves. And so why is it that actually these mechanical oscillators are used, say, in science, technology, and precision measurements? And in science technology, the reason it's used is that compared to the speed of light, the speed of sound is much slower. So you can make actually devices that have gigahertz of frequencies in just minuscule kind of volumes that you can also use then in your F-bar filter cell phone applications. So it's this fact of this low speed of sound compared to speed of light, and also the large quality factors, so the very low dissipation of systems, that have given rise to these applications. Now, in all these applications, actually, be it LIGO or other classical information technologies, the mechanics essentially is classical, okay? But we all know from just quantum mechanics that mechanical oscillators can also be quantized. And so if you have, for instance, a mechanical oscillator, say, that has a 1 megahertz mechanical frequency, okay, you know actually that there's a quantum mechanical ground state, and that ground state has a zero-point fluctuation and gives rise to mechanical zero-point fluctuations, so an uncertainty in the mechanical oscillator position. If you ask what does it take to place this mechanical oscillator in its quantum ground state, well, you need a temperature, okay, to freeze out all kind of the residual quanta in the system, actually of 50 microkelvin. And so these are temperatures that are far below actually what you can use and create in cryogenic cooling. At the same time, if you want to measure the motion of a macroscopic mechanical oscillator and observe its zero-point fluctuation, it would require you, say, for an AFM cantilever, to make a measurement that can resolve a thousandth of a proton radius. So these are very small, minute displacement kind of that you have to resolve. And so what are the challenges to extending kind of control to macroscopic mechanical oscillators? The challenge is, first of all, typically mechanical oscillators have low frequencies, megahertz and gigahertz, so you need very low temperatures. At the same time, you need very sensitive readout typical order of magnitude is a thousandth of a proton radius, as I mentioned. And also you somehow need to couple to the mechanical system, satisfying the dichotomy on the one hand to have a system that's very pristine, isolated from the environment, but at the same time coupled to a readout apparatus. And so these three have been formidable challenges that have been existing for about 20 years, but they have been solved. And they have been solved in particular in the field of atomic physics. So in atomic physics, it's very well known that you can use radiation pressure to trap dielectric particles or also atoms, as pioneered by Stephen Chu at Bell Labs with Art Ashkin. You can also use radiation pressure of light to cool atoms, and it's of course very well known. It's a field of atomic laser cooling, and this goes back to ideas of Hans Demelt, Shallow, Hensch, and others in Wineland to use actually the radiation pressure of laser light to bring to standstill atoms. Okay, and this has been achieved, for instance, in the context of trapped ions by Dave Wineland or in '89. And so you could bring an ion in a motional trap to complete standstill at a low vibrational frequency by using laser cooling. So by using the fact that an ion has an internal two-level system transition that can be addressed with laser light. And just a little historical remark, the original proposal of atomic laser cooling actually shown here was just a little abstract at a conference that comprised a mere 100 words by Demelt. Now, so the question is, can you also use similar ideas, so laser manipulation, but extended to macroscopic mechanical oscillators? And that's really what the field of quantum optomechanics has studied for the last 2 decades, and that's actually what today is a practical reality. And so, much of the motivation really is, can you take this quantum control of atoms and ions and actually achieve, say, superposition states of mechanical oscillators and thereby achieve quantum control over macroscopic degrees of freedom. And there are a number of motivations to do so that I'll outline at the end, but primarily, as I said, it's an endeavor and quest of precision measurement and precision control, understanding dissipation in these systems and also how to control them by laser light. Now, there's a nice kind of colloquial saying that for kind of every invention made in the Western world, there's at least one Russian who thought about it before. This actually is also true for atomic laser cooling. So as I described, or in '75, Hensch and Demelt and Wineland and others actually proposed atomic laser cooling. But it turns out actually that during the UdSSR, there was one more scientist who was really a thought leader in the quest of gravitational wave, and that was Vladimir Brzezinski. And Brzezinski, already back in 1970, so this precedes atomic laser cooling by almost 5 years, published a paper in Russian that was later translated by Kip Thorne at Caltech to English, and it was called Investigation of Dissipative Quantum-Motive Effects of Electromagnetic Radiation. And so what sounds as a bit of an obscure title was a paper that was concerned with a very simple measurement apparatus that all of you can now recognize as being the principal component of gravitational wave interferometers. And it was simply a test mass, in this case a mirror, that is thought conceptually to be mobile, so it can move. For instance, it can move due to the response of an external force. And this is coupled actually to a cavity. Okay, these are the 2 mirrors. And in between this cavity can either be a microwave field or an optical field. And so what this device is, it's a parametric transducer. It transduces the small fluctuations x, the position of the mechanical oscillator, actually to an optical observable, and this is, in this case, the phase fluctuations actually of the laser light that's reflected actually off the mirror. And so what Brzezinski actually was worried about is that on the one hand, this system, which can be used to make very sensitive measurements actually of mechanical motion, at the same time opens a channel actually to a measurement back action. And this comes from the fact that photons inside the cavity are quantized. There's a radiation pressure quantum fluctuation that will stochastically drive actually this mirror. And this actually causes there to be an innate uncertainty in the mirror position. And he termed this the standard quantum limit, okay, the SQL of mechanical displacement sensing. Now, there's something else he discovered actually while looking actually and by analyzing the system. And this can be understood very simply by noting that photons that travel between these 2 mirrors have a certain photon storage time. So they don't immediately escape the cavity after having interacted with the mirror. And this actually is precisely what links to this title of this paper, Dissipative Quantum-Motive Effects. What Brzezinski realizes is that in this system, if the radiation pressure force that acts on a mirror, so every reflection of a photon gives 2 h bar k momentum transfer, if there's a delay in this radiation pressure force due to the finite storage time, one can actually make the radiation pressure force viscous with the mechanical motion. And that means actually the force acting on a mirror, it can either actually be in phase or out of phase with mechanical motion. And thereby, actually, depending on the sign of the detuning of the laser, it can either amplify the motion of the mirror, or actually it can remove energy and cool. So why was Brzezinski thinking about this effect? He was actually very worried, actually, about the observation that laser light can amplify mechanical motion. And why was he worried? He was worried, actually, that this could render the entire gravitational wave observatory unstable, because you amplify mechanical motion and generate an instability. So the system would act effectively as a laser, but not for light, but a laser for phonons, a phonon amplifier. So that was his observation. Now, it suffices to say that in modern gravitational wave interferometers, the test masses are kind of kilogram. And you can compute that the threshold for these regenerative oscillations is so high that practically, actually, it is not a limitation. So you can also formulate a quantum theory of this effect, and thereby derive kind of the primitive interactions that this radiation pressure coupling allows. And so these are some of the few formulas I want to show. So again, very simply, if you have two mirrors and you have radiation pressure, okay, photons transfer 2h bar k momentum transfer, you multiply by the flux, okay, you can re-express it as a number of photons times a coupling constant g, which tells you how much frequency shift the cavity moves as a function of displacement. And if you simply multiply the force by position, then actually you can obtain the radiation pressure quantum mechanical Hamiltonian. And this Hamiltonian has a number of interesting features. The first is that it couples the intracavity photon number, so A dagger A, to the mechanical oscillator position. So if you look and squint at this expression, this actually is a three-wave mixing expression. It has three operators. And in typical optical experiments, what you would do is you would drive the cavity with coherent state, and you can linearize the system and arrive at this bilinear Hamiltonian. And this bilinear Hamiltonian, okay, comprises terms of the optical field, so A and A dagger, so this is actually the optical quadrature, and B plus B dagger, the mechanical position. And they're coupling actually by this so-called vacuum coupling rate. Now, if you look at all the possible terms that this interaction Hamiltonian gives, it becomes immediately evident that this radiation pressure interaction is an incredibly powerful and precious toolbox. Okay? And you can see kind of why. So if, for instance, your optical laser field is detuned exactly by the mechanical frequency above the optical cavity, you have a Hamiltonian that you call the amplification or two-mode squeezing Hamiltonian. It will actually generate a photon inside the cavity while emitting a phonon. So it's a parametric down conversion, but not actually for photons, but for a photon and a phonon, a mechanical vibration. At the same time, if you take the system and detune it actually onto the red, you can annihilate one quanta in the mechanical oscillator while emitting a photon of higher energy into the cavity. And this is actually an anti-Stokes process giving rise to cooling. And this is in quantum optics language actually called the beam splitter Hamiltonian. And these two Hamiltonians together actually provide you the full toolbox of quantum control of mechanical systems. So what can you do with this toolbox? You can actually achieve ground state cooling of the mechanical system. You can achieve coherent coupling of photons and phonons. You can generate quantum motive squeezing. You can generate entanglement between mechanical oscillators and the light field, or you can also squeeze actually the mechanical system itself. So it's a toolbox that allows you, granted that your cavity decay rate is much smaller than the mechanical frequency, to achieve quantum control over mechanical systems. So much of this quantum theory is very well understood, but let's take one more time a look actually back at the original thoughts that Brzezinski was formulating. So Brzezinski was interested mostly in the quantum effects of radiation pressure and worried about this classical dynamical backaction. So dynamical backaction refers here to the fact that the detuned laser leads to either an amplification of mirror motion or a cooling. Now, it turns out actually that LIGO observed very recently actually the parametric instability. Well, it's not so recent, but it was first observed in 2015 that the mirrors actually went unstable due to a coherent phonon kind of lasing of the end mirror modes. But the first system in which this radiation pressure interactions as this cooling and also amplification was observed was not in these macro scale experiments, but on the micro scale. And it's quite evident why. So this is one of the systems that we used as a kind of a building block, so to speak, in our experiments. And this is an experiment that was done actually when I was a grad student back at Caltech. And so it shows actually a so-called optical microresonator. And so these are devices where light kind of continuously recirculates. The diameter here, didn't put a scale bar, is typically actually a few tens of microns, so a fraction of a human hair. These cavities actually have one unique property. They have incredibly long photon storage time. So you can wrap about 100 meters of path length into a device that is a fraction of a human hair. And so these have so-called quality factors of well above 100 million. Now, this system is not only an optical resonator, made in this case from glass, but also, just like a wine glass has a mechanical mode, this device actually has an acoustic vibration. And this acoustic vibration has a frequency of a few tens of megahertz, so it's much faster than the photon storage time, which is needed to access this radiation pressure cooling and amplification processes. And it's innately coupled to the radiation pressure field. So in some sense, any optical resonator is a perfect kind of innate optomechanical system. It has an optical resonator and mechanical resonator at the same time. And radiation pressure actually couples to the 2 degrees of freedom. So this system actually allowed us about 15 years ago, actually, to observe radiation pressure and stability, and also to observe cooling of mechanical motion. So if you actually place the laser on the red sideband, photons actually that are scattered into the resonator can only do so by removing actually quanta from the mechanical oscillator. And this laser cooling, quite strikingly, does not heat the mechanical oscillators. Although photons can get absorbed, the dominant effect actually is to reduce the temperature, the effective temperature of one mechanical mode. And this actually works exceedingly well, so you can cool mechanical systems, including these vibration of these dilatation mode resonators, to the quantum mechanical ground state, and you can show that a technique actually can reach the ground state with residual thermal occupancy. So over the last decade, these techniques of amplification, so sideband amplification, sideband cooling, and the combination of the two have led to an extraordinary series of experiments actually in the field. And so today, you can take these whispering gallery resonators, small drum hats, photonic crystals, or just membranes, and prepare them in the quantum ground state, generate entanglement, generate squeezing, and also make extremely sensitive measurements actually of mechanical motion. Moreover, there have been numerous kind of advances also on the theory side, how to use these interactions of phonon and phonons to, for instance, create new kind of phases of light and sound. And so, so today, actually, the quantum mechanical control of systems is really reality. So one can achieve ground state cooling, one can entangle 2 drums that are, in this case, 2 vibrations of 2 aluminum plates. One can also couple mechanical systems to qubits, and thereby also open up a channel for generating non-classical states. One can generate quantum memories with exceptionally long coherence time, and also use these optomechanical systems as transducer from the microwave to the optical domain. And there are even ideas actually of how to use this enhanced control of mechanical systems, even for gravity searches and dark matter, by generating a superposition states of a mechanical oscillator state and looking how this is actually decohered by the gravitational field. Now, admittedly, these experiments, particularly using mechanical systems for gravity wave detection, are still very far out. But the important point actually is that systems have progressed to the point where in the next decade, such experiments actually become feasible because technology to achieve quantum control actually has been well developed. Now, another aspect that these optomechanical systems allowed is actually really a revolution in our ability to measure displacement. I want to draw your attention to the enigmatic zero-point energy that all of you know from quantum mechanics. And so the question you can ask yourself is, can you build a displacement transducer capable of measuring the vacuum fluctuations of a mechanical oscillator if, say, you had prepared it in the ground state? And as alluded to earlier, you need exceptional displacement sensitivity. And in fact, much of the 2000s, there was numerous efforts in the world to make very sensitive electrical transducers to measure mechanical displacement and to allow it to reach this yellow line, which actually is the vacuum fluctuation of a nanomechanical oscillator. Now, over the last decades, due to these advances made in optomechanics, it has been possible to create displacement sensors that operate actually far below this yellow line here, which is called the standard quantum limit. In fact, the latest devices from Albert Schleicher's group in Copenhagen are operating more than 60 dB, so 6 orders of magnitude below actually the zero-point fluctuation. And that means that these experiments are really realizing the original thought of Heisenberg, a Heisenberg microscope, okay, and even some of them at room temperature. So the product of imprecision, okay, so the uncertainty in the mechanical position is now so far below the vacuum level that actually the back action, so the momentum fluctuations imparted by the measurement process start to dominate even over the ambient fluctuation around room temperature. And so I should mention that This chart here was actually plotted by my PhD student, Vivek Sudhir, who's now assistant professor at MIT. And what's still quite astounding is the many orders of progress made actually just in 1 decade. And I think it's quite rare in physics. You see 5 orders of magnitude in just 10 years of any quantity that one considers. So here it's basically a 5 order of magnitude improve in less than a decade in displacement sensors. So let me give you one concrete example of how these experiments look like from our own research at EPFL. And so the first experiment I'd like to invite you to consider is a sensor capable of measuring the motion of a nanomechanical string. And so what's shown here in red actually is a string, a very simple string that's double clamped. So you can solve Euler-Bernoulli's equation, you can find the fundamental vibrational frequency, okay, and you can compute also the zero-point fluctuation, okay, of this mechanical oscillator, h bar over 2m omega. Now, so in order to measure the fluctuations, what we do is we don't build a macroscopic interferometer, but rather what we engage in is to use an optical cavity, okay, an optical microresonator, as a way to very sensitively measure the displacement. And we do so actually by using near-field coupling. So we place the mechanical oscillator just a few tens of nanometer away from the optical mode, that's color-coded here. And so any vibration of the mechanics changes the optical path length and thereby allows us to measure the motion of the mechanical oscillator. Now, to give an example of what exquisite sensors you can make, let me give you one example here and be concrete. So what you can ask yourself is, if this mechanical oscillator was cooled to the ground state and had only vacuum fluctuations left, how much actually frequency shift would you have in the optical cavity? And so if you compute that number actually for this experiment, the so-called G0, this is about 15 kilohertz. And so for those of you who are familiar with laser physics, actually 15 kilohertz is a very large number. It's much larger than a typical line width of most lasers. So these sensors, okay, allow you basically to create a 15 kilohertz measurable signal due to the vacuum fluctuations of the mechanical system. So this implies you can make exceptionally sensitive sensors. So you can also compute what is the imprecision and so the power necessary inside the cavity to measure, okay, at the standard quantum limit to resolve the zero-point fluctuation. And in these sensors, what's striking is that even on average, just one intracavity photon on average allows you to reach a measurement sensitivity that's sufficient to resolve the zero-point motion. So these are exceptionally sensitive sensors. And why is that? Because in contrast to LIGO that uses kilogram mirrors that are 4 kilogram, these mirrors here are just picogram. So it's the reduction actually in the mass that boosts the zero-point fluctuation and actually makes the coupling by using very small kind of gaps between the optical field and mechanical oscillator very large. So what can you do with these systems? You can measure displacement. So here's an example where the mechanical oscillator, okay, the in-plane, out-of-plane mode actually of the mechanical system are measured. You see here, so our noise floor, you see the in-plane and out-of-plane motion of the mechanical beam. You see also other mechanical modes that we push to high frequency, not interfere with the measurement process. And what we can do is we can ascertain the measurement sensitivity. And again, this yellow line shows the SQL, the expected contribution from vacuum fluctuations. Never mind, this is a room temperature experiment, so a mechanical oscillator is in a highly excited state and has at 4 Kelvin about 10,000 quanta. And what we can ascertain here is that we're actually measuring more than 40 dB below the standard quantum limit. So we're making a very precise measurement of mechanical motion. And what is the effect of making such precise measurements? The effect is that our total noise budget, so if we look at the motion of the mirror, or the nanomechanical oscillator, it contains a contribution from the environment, that's just a thermal noise, about 10 to the 4 quanta at 4 Kelvin. But also we start to see that as we measure more strongly, we start to heat the oscillator. And this heating is not a heating due to the laser heat in the cryostat. Actually, it's a radiation pressure quantum fluctuation stochastically driving the system. And so we see here this limit that actually was originally thought of by Brzezinski. And we can make measurements here far below the SQL. And so, so what can you do with such sensor? So one example is you can use the measurement record to feedback cool the oscillator very close to its quantum ground state. And the way to do that is using a very simple measurement technique from atomic force microscopy, which is you measure the phase of a light using a homodyne interferometer. You take that measurement record, you delay it using a BNC, so just you impart a viscous feedback, and you act back on a second laser that acts with a force on a mechanical oscillator. So it's a very simple feedback experiment where the force is proportional to the x dot, to the position. And if you do that, you can actually cool the mechanical oscillator actually down to very low occupancy. In this case, the lowest occupancy that we achieve is about a 15% ground state occupation. And if you cool further, actually you start to feed the noise actually into the mechanical oscillator, which leads to so-called squashing. So these experiments, at first sight, they look just like classical experiments that we know from classical engineering, just the feedback control of a mechanical systems. But what's actually very striking, that this type of feedback is not ordinary feedback, but it's quantum feedback. And why is that? Because the very act of making a measurement imparts stochastic noise in the mechanical system. And if you look at the final occupancy we obtained in this experiment, so in this case about 5 phonons, about 16% ground state occupation, it turns out that the act of measurement, by realizing this Heisenberg microscope, has generated more than 2,000 quanta in the system. So we're so strongly measuring the position that there's a very strong momentum uncertainty. Now the question is, how can you see actually that you're operating this regime? And just from feedback experiments, you can't. But what you can understand is that the act of measurement generates this so-called measurement back action. And this measurement back action is effectively the quantum fluctuations imprinting itself on the mechanical oscillator. And what this actually gives rise to is squeezing. And so here is the same experiment, one more time, by just looking at the output of light that has interacted actually with this optomechanical system. And when you send a coherent state actually inside this optomechanical system and make a strong measurement, the light actually that emerges from the system is squeezed. And this squeezing implies that the vacuum fluctuations of light actually in one quadrature are reduced below the vacuum level, and in an orthogonal quadrature they're above. And so in this case, the squeezing is entirely achieved actually by just the measurement itself, by operating in a regime where the quantum fluctuations of the light field start to dominate over thermal sources. So in this experiment, the amount of squeezing we obtained was very modest, just a few percent at cryogenic temperature. But there's ways to improve it, and I'd like to explain in detail in the next minutes how you can observe these effects of squeezing of light on room temperature mechanical systems. Now, first, the question, of course, that I'd like to briefly mention is, what could this actually effect be used for? And the squeezing of light in optomechanical systems has also been considered in gravitational wave observatories. And here, this effect has a name. It's called quantum variational measurements. And the idea is to use the mechanical response of the end mirrors to squeeze the intracavity light field and thereby actually enhance the sensitivity to an external force. And so the ability to achieve radiation pressure squeezing at room temperature actually would render gravitational wave interferometers, for instance, more sensitive, okay, due to their power limitation in the handling power. And so what we have realized effectively is a tabletop version of this experiment, like a mock-up version, a proof of concept, that we can actually use optomechanical system as quantum variational force measures. Now, how can you achieve these effects at room temperature? Now, the observation of the squeezing that I described was a cryogenic experiment, and we reduced the thermal occupancy and thereby the influence of Brownian motion by about a factor of 100. So how can you achieve the same also at room temperature? And for this, what you primarily need is mechanical oscillators that have exceptionally high Q, so very, very low intrinsic innate dissipation. And so what I show here actually is a device that's fabricated in our lab, which is a very thin silicon nitride membrane, okay, that is only 20 nanometer thick, so you can actually see through it. The dimension here is about 5 by 5 millimeter. And what you also see is a corrugation, okay, that is used to confine phonons into its center. And so how can you make membranes with exceptional low dissipation? Also this actually, so when you, first of all, when you look at the subject of dissipation, and you look at all different mechanical oscillators, be it mechanical systems in timekeeping, atomic force cantilevers, or even carbon nanotubes, what you find is there's in general a heuristic scaling of the quality factor of the system with the volume, with the size of the system. And so what's quite striking is that starting about a decade ago, the field of optomechanics made incredible progress of making exceedingly high Q mechanical oscillators. And so today we have systems that at room temperature have quality factors of more than 3 billion at megahertz frequency, and at cryogenic temperatures as high as 15 billion. And so these are even more coherent than macroscopic bulk sapphire oscillators that were investigated for gravity wave detectors in the 80s and 90s based on bulk systems. So we can make nanomechanical systems that are the most coherent systems, actually, of mechanical oscillators of any kind, of any material. So how does this work? It uses an idea that actually also was formulated in the community of gravitational wave detectors. If you look at how the test masses of LIGO are suspended, they're suspended actually on rods in a gravitational potential. And so what this gravitational potential does actually is, to this energy stored into the system, it adds that there's not just energy in the elongation, energy in the bending, but also energy in the elongation, in this case in the gravitational field. And by making the energy in elongation actually very, very large compared to the one in bending, by just making a very heavy kind of test mass, you can increase actually the mechanical quality factor. And for those who play music instruments, this is maybe well known, but there's many subtleties of this effect. And for condensed matter physicists, actually it's quite striking because the intrinsic acoustic dissipation of the material can be diluted. You can obtain materials in whose body acoustic waves are quickly attenuated, but by placing the material in a very high stress, you can actually increase the mechanical quality factor. And so these ideas we have explored not by using a gravitational potential, but by strain, by using materials that under the position conditions are highly stressed. And this is an example of what you can achieve with such devices. This is a strained piece of silicon under about more than a gigapascal stress that we achieve, and we use here a phononic corrugation to localize a defect mechanical mode in its center. And by localizing the mechanical mode in a medium with very high stress, we are able to achieve quality factors here that at room temperature above 1 billion and at moderate cryogenic temperatures of a few Kelvin reach 13 billion actually of quality factors. So these are remarkably kind of coherent mechanical systems that we can generate. Now, these 1D systems are not optimal to couple to optical fields, and so what we do is we use instead two-dimensional membranes. In this case, it's a membrane, a square membrane, again, by showing this millimeter scale here, that is density modulated with very small pillars to confine actually a phononic localized excitation in the megahertz frequency range right at its center. Now, these devices at room temperature can, again, by making use of strain, can achieve quality factors of more than 100 million actually in ambient temperatures. And so if you now insert those in optical cavities, you can also explore quantum optomechanics at room temperature. Now, one of the challenges, however, is not only to measure the mechanical motion, but also to discern the motion from other extraneous influences in the experiment. And so, for instance, if you want to measure a signal that's on the order of the vacuum fluctuation of the mechanical system, you need to ensure that the signal imparted by the mirrors themselves, the extraneous classical thermodynamical noises, are also made small. And so in this experiment, by actually creating a phononic mirror, so this is a mirror actually with here a periodic segmentation, we can create an exceptionally quiet region of frequency noise by making use of phononic band gaps on the top and bottom mirror. And quite strikingly, actually, these mirrors still retain actually their high optical quality factors for their optical reflection. And so we're making here very quiet regions of frequency noise. We can actually observe here room temperature squeezing, in this case actually more than 2 dB, in an optomechanical system on a tabletop experiment. So it shows that optomechanical squeezing can also be actually generated in room temperature environment. And if this was, for instance, achieved in a LIGO type of experiment, you could directly use it for quantum enhanced kind of sensing. So in the last part of my talk, I want to talk about another way that I find personally very fascinating when I entered this subject some 2 decades ago. And that was the question, can we not generate squeezed states of light, but can we generate squeezed states of mechanical systems? So a mechanical oscillator whose vacuum fluctuations are reduced in one quadrature and enhanced in the other. And in fact, this is possible now with the techniques that I've described, with the techniques of optomechanics. And the experiment I'd like to describe here is also a membrane, but it is a membrane made out of aluminum. And this membrane is hovering on top actually of a ground plate and forms actually a capacitor. And if this capacitor is hooked up to an inductor, an LC circuit, you make the resonant frequency of the LC circuit frequency dependent. And so you again have an optomechanical system, but actually realized in the microwave domain. And so what we can now do is we can cool this drumhead of a few megahertz of frequency to its motional ground state and play a trick by using both blue and red sidebands to actually cool the system into a squeezed states of motion. And so the way this works again is we have our vacuum gap capacitor. It's coupled to an inductor. We can send microwave fields in to excite the LC circuit and measure the mechanical motion. And now the first thing we can do is, for instance, we can cool the system into its motional ground state. And the way we do that is by using a laser that is basically redly tuned from the optical cavity. In this case, it's a microwave cavity. We can scatter photons actually into the cavity, thereby removing mechanical quanta from the system, and cool this drumhead capacitor into its motional ground state. The intrinsic temperature of this drumhead capacitor is millikelvin, so it's taking place in a dilution refrigerator. We benefit here from the very good quality factors actually of these drums. So again, we make use of this trick of strain engineering to achieve quality factors here of 40 million, which corresponds to a kind of a decoherence rate on the 50 millihertz level. Now, taking the system, the first thing you can do is initialize it into the quantum ground state. And one of the questions is, how can you assess if the system is indeed cooled to these very low occupancies? And here we use a trick that is very well known actually in the field actually of Raman scattering on solid-state molecules or phonons in condensed matter. If you use two probes that have equal strength, and you look at the scattering rates into the cavity, one of them actually will have a proportionality with n plus 1, where n is the number of quanta in a mechanical oscillator, 1 is the commutator, and the other one with n. So there's a quantum mechanical asymmetry in the scattering rate. And this you can use, for instance, in Raman thermometry to determine temperature. So here we do Raman thermometry on these microscale mechanical oscillators by scattering sidebands into the cavity and looking at this asymmetry that starts to appear as we cool down the mechanical oscillator. And for the purpose of making the readout independent of the cooling, we have a second cooling tone that's detuned. Now, if you do that, you start out and you start cooling the mechanical oscillator, and you start to increase the cooperativity, you start to see an imbalance appearing between red and blue, showing you that you're approaching the quantum ground state. And at the lowest occupancy, you see a complete vanishing, actually, of the red compared to the blue sideband, and this shows you that actually we're deeply in a quantum ground state. In this case, we have initialized the mechanical oscillator, which is more than 93% actually in its motional ground state. So this is still a very classical state. It's thermal. It's just the ground state of the oscillator. We can also see how quickly the mechanical oscillator heats up by performing so-called quadrature measurement and seeing actually how quickly the oscillator rethermalizes. We see actually it's heating up with 6 milliseconds of decay time. Now this implies that for a time frame of a millisecond, you can prepare a non-classical state and keep the system sufficiently well decoupled from the environment to keep it in that state. And so how can you generate a squeeze states of mechanical motion? The squeeze states of mechanical motion uses a principle by which we generate and use both a red and a blue sideband pump. As I described, a red sideband pump will actually be effectively a beam splitter Hamiltonian, a blue sideband pump a parametric down converter. And if you combine both, in fact, the Hamiltonian of the system actually couples the mechanical oscillator or the optical field to the so-called Bogusław mode. And so you have here an operator that includes both B and B dagger, and the eigenstate of these operators, they are squeeze states. So this protocol that was proposed about a decade ago by Cromwell allows actually to generate squeezing actually by making, in the presence of two kind of tones, often blue and then actually in the red sideband. So by doing this, actually, we can generate, in this case, about 5 dB of squeezing. So the vacuum fluctuations are reduced by 5 dB below, actually, the ones for the corresponding for the vacuum state. And you can also track how the mechanical squeeze state thermalizes to the environment, and showing us, in this case, a lifetime of 2.3 milliseconds. And so this is an example of using the optomechanical toolbox to generate non-classical states of light, non-classical states of mechanical motion, and also watch actually them decohere due to the interaction with the environment. Now, so we can also track this here and see actually how the squeeze state starts to thermalize once we actually turn off the tones. And we see here that we can keep for more than almost 2 milliseconds a squeeze state in the presence of its coupling to the environment of the system. So again, this shows kind of the very exquisite control that the field of quantum optomechanics has actually achieved on mechanical systems. And what can you do? And what is the ultimate kind of, what are the possibilities that are afforded by these interactions? First of all, much of the motivation of quantum optomechanics is purely fundamental. It's really a question, can you achieve quantum control of a mechanical system? But there are some examples, actually, where also this interaction can be used in a somewhat useful way. And for instance, one example is you can create thermometers that are using quantum noise at room temperature, and thereby can calibrate temperatures actually with the vacuum fluctuations of the optomechanical interaction. You can use mechanical systems as links between the microwave and the optical fields, which are still two frequency windows that are hard actually to connect directly. And also you can couple the mechanical systems to other quantum systems, such as superconducting qubits, and possibly use them actually as memories. Other examples actually are to use the optomechanical interaction, for instance, make non-reciprocal devices for the microwave field, for the optical field, that are used actually ubiquitously in measurement chains to prevent actually noise from backpropagating. And one application I personally like a lot actually is this example here by Albert Schliessler group in Copenhagen, where a nanomechanical oscillator was used to measure RF fields, purely optical. And this can be very interesting for an environment, for instance, where you have very high magnetic fields. And in their application, they were inserting such optomechanical displacement sensor actually in an MRI for improved pickup actually of the RF fields generated by the nuclear spins. And last but not least, one aspect that I think is still many decades out, but it's still, I think, very fascinating that we're actually approaching this regime, is really to ask, can we place mechanical systems, or macroscopic oscillators, in superposition states, such actually that one can test quantum gravity? And I think today we're still probably many decades away from this, but the prospect of it is not entirely unrealistic, given our ability now to generate very, very coherent mechanical oscillators, to actually manipulate them at the quantum level, and ultimately also generate these non-classical states of motion, superposition states that are either Schrödinger-Cat states, or for instance that are superpositions of 0 and 1 phonon, and actually then verify, does the system decohere actually with a time frame that is commensurate with the predictions of quantum gravity. Again, very, very many decades out, but I think we have laid the foundations actually to start to take such ideas also more serious. With this, I'd like to thank you for your attention, and I apologize for changing the title of the topic, but I want to talk about something that I feel very passionate about, which is precision measurements.